Hello, today we're going to be working on lesson 6.1 in chapter 6. It's all about discrete probability distributions. So in chapter 5, we were talking about probability, and those probabilities were discrete as well. Discrete meaning they had to be whole outcomes, like a whole house or a person or an animal or a car. And so in chapters 5 and 6, we're talking about discrete random variables. We're going to move into continuous data in chapter 7 through 12. So let's just review the difference between discrete and continuous variables. So example 1 here. I want me to pause it and take a minute and go through each of these A through E and decide if they are discrete or continuous. Now that we're back, we would see that the 20-sided die is discrete. The height is continuous. The weight is continuous. They're both measured. Number of songs is discrete, and length is continuous. So these things are all measured. That's why they're continuous. Okay, so a probability histogram. We have actually looked at these in chapter 2 and a little bit in chapter 3. You just didn't realize it. It's a histogram where the horizontal axis corresponds to the value of the random variable, and the vertical axis represents the probability of each value of the random variable. And probability meaning essentially the relative frequencies that we did in chapter 2. So this first example here, the NBA Finals, is a best-of-7 series. The following table shows the number of games that have been played in every NBA Finals from 1947 to 2019. The following is a frequency distribution of the data. So to win a series in the NBA, it says best-of-7, meaning if you have 7 games, 1, 2, 3, 4, 5, 6, 7. The best meaning you'd have to win 4 of them, 4 of the 7. So the first team to win 4 of those 7, so they could win the first 2 and the last 2, or they could win the first 2 and skip 1 or 2 and win the next 2, or they could win the first 3 and then somewhere down the line win the 4th one, but they have to win 4 to get a majority of the games. Sometimes teams win the first 4 games right away, but sometimes it takes all the way to the 7th game where they each have won 3 and 3, and the 7th game is a deciding factor. So this is the data that we have. 27 times it took 6 games to decide the NBA champion. Okay, so it's asking us to find the probability of these. So to find the probability, if we go back to probability in chapter 5, it says the number of occurrences out of the number in the sample. So the total number of games that we have here is 73. And so to find this probability here, we take the number 9 and divide it by 73, and we get 0.123. And then likewise, 18 divided by 73, and we get 0.247. And then 0.370, and then 0.260, and these should equal to 1.0. So this is what our frequency histogram looks like. So this is the number of games. It says, what does the area of the 4 bars add up to? It should add up to 1.0, and describe the shape of the distribution. So it's not very telling, but it does look a little bit skewed left. And then it says, explain why this probability distribution is considered discrete. And that's because you cannot win part of a game. You may be able to tie during regular season, but you cannot win part of a game during the playoffs. Okay. So page 161, at the top here, goes through the 2 rules of a probability distribution, which we learned about in chapter 5 as well. So this one means that the sum of the probabilities must add to 1. This one here means the individual probabilities. So individual probabilities must be greater than or equal to 0 or less than or equal to 1. Both of these have to be satisfied. So in example 3, it says determine whether the table represents a valid probability distribution and explain each case. So I'd like you to pause the recording and go through each of these scenarios and see if it meets both of these criteria. And I'll be back. So this first one does. The probabilities add to 10 over 10, and each are positive but less than 1. B is a yes. They add to 1, and they're each greater than or equal to 0 and less than or equal to 1. C is no. We cannot have a negative probability. And D is a no, because the sum of the probabilities is greater than 1. So to find the mean of a discrete probability distribution, it's very similar to the weighted means. So let's just, similar to chapter 3.3, weighted means. And what we do is we take the outcome times its probability, and then we add all of those products up. The standard deviation is the square root of those, the product of the outcome squared times its probability, subtracting the average squared. We are not going to have to calculate these by hand. We're going to use StatCrunch. Okay, so we call this the expected value of the outcome. In other words, with a certain number in our sample, we would expect a certain outcome. So let's go back to the NBA data, where these are the number of games possible to win a series, and these are the probabilities, and we want to compute the mean and the standard deviation. So let's just go to StatCrunch for a moment. And here we are. And this is, we're getting a new data set here. So I'm going to label this number of games, and this is going to be probability. And you can find this data set in course pack 6.1, page 162. So I'm going to have that saved for us here. So that'll be available for you to use, to go back to. So we have 4, 5, 6, and 7 are the games available. And we're going to enter the probabilities here. And then to find the weighted mean, similar to what we did back in chapter 3.3, is we're going to go to stat, and we're going to go to calculators, and we're going to go all the way down to a custom calculator. See this at the bottom here under calculators, a custom calculator. And our values are in number of games, our weights are in the probability, and then we can hit compute. And it gives us the mean right here. So does everybody see that highlighted? So the mean is 5.767. We can round that to 1 decimal of 5.8. And the standard deviation is 0.97. And then it says, interpret the mean and standard deviation in the context of the situation. So we can go back to our paper to make sure we're all writing down the same thing. So interpret, so it says, we expect the NBA Finals to be won in 5.8 games, comma, give or take 0.97. Okay, that's one example. Now, when we're talking about probability, or let's say you have an investment business opportunity that you might want to invest in, and there's different possible outcomes, like it might be successful or not successful or so-so successful. We want to find out what is our overall expectation for profit, and that will kind of help you decide if a business is going to move forward on something or not. And so that is called the expected value or the expected outcome. Okay, it's a mathematical way to use probabilities to determine what to expect in various situations over the long run. If you become an actuary, it requires a lot of mathematical schooling and some test taking along the way, but you can work for insurance companies to help them do the statistics in the background to decide what the different likelihoods are of different age groups for getting in car accidents, or how long they might live, or the value of jewelry and things like that. So this example we have here is amount of the claim. This is on insurance claims, on automobile insurance. Okay, and this is ages, drivers 16 to 21. And this is a probability of their this claim amount happening. So there's about an 8% probability that they're going to have a claim of $4,000, this age group of 16 to 21. So it says, explain why this is a valid probability distribution. And we can say because the individual probabilities are between 0 and 1 inclusive, and the sum of the probabilities equals 1. Explain why this is discrete. Okay, so we cannot have part of a claim. And we're going to say in dollars because this is in dollars. Okay, so here they're treating dollars as discrete. Normally in monetary, we probably treat it in a way continuous, but in this case, it's a discrete level of where they fall. Calculate the expected value of the distribution and determine what the expected value means in practical terms. Okay, so we're going to go and put this into StatCrunch. And we're going to do a new data table. And we're going to call this amount of claim. And this is going to be the probability again. And we're going to just enter these. And then, as we did before, we're going to go to Stat. So to Stat and Calculators, and we're going to do a custom calculator down at the bottom. And amount of claim is our values. Our weights are in the amount, the probability. And then we're just going to hit compute. And there's our mean and our standard deviation. Okay. So the mean is $1,100. The expected value is $1,100. And so it's asking us to, let's go back to that. It's asking us to determine what the expected value means in practical terms. So a driver age 16 to 21 can expect to have car insurance claims of $1,100, give or take. And the give or take was a lot, wasn't it? It was 2,027. Let's just go back and validate that. So calculators, custom, and a claim, probability, and compute. And there it is, $2,027.31. How much should the company charge as an average premium so that it makes a profit? Well, they're going to want to at least charge the $1,100, right? Because that's what most of these drivers on average are having accidents that cost this much. So we'll say $1,100 or more. If the company has 10,000 16 to 21-year-old customers, which they charge an average premium of $1,500, how much profit does the company expect to make? Well, each customer, if you take 1,500 and subtract the 1,100 that they say it's going to cost, their charges are going to be, right? The premium, the charges are going to be, they're making $400 for each. So they would take 10,000 customers and multiply by that $400 profit. And it looks like they're going to be making $4 million. That's a lot of money. Okay, let's check out another one of these scenarios. So page 164 has data in. And they gave us 3 situations. It says an oil company is considering 2 sites in which to drill, described below. So they have site A has a profit of $80 million if they find oil. If they don't find oil, they lose 10 million. That's important to know. Losing means it's going to be negative, right? And the probability of finding oil is 0.2. Okay. Well, to do these outcomes, we have to know the probability of each outcome. So let's just look at site A setup. So we have an outcome, we have a profit, and then we have a probability, right, of each outcome. So the outcome is either they find oil or there is no oil. We hope we find oil. So if they find oil, there's an $80 million profit. And the probability of finding oil is 0.2. And then if no oil is found, they lose 10 million. And I'm just putting in M for millions. But the probability of not finding oil means that's going to be 1 minus the 0.2, which is going to be 0.8. So that's what we would enter into the calculator. Okay. Now let's look at site B and the same thing. And we'll find each of their expected outcomes. Okay. So we have the profit here. Profit, if they find oil, is 120. And their loss, if no oil, is, and so they're losing 18 million. Probability of finding oil is 0.1. So that means not finding oil is 1 minus 0.1 or 0.99. And then site C, so they have, if oil is found, they have a profit of 70 million. If they don't find oil, they lose 5. And the probability of finding oil is 0.15. That means the probability of not finding oil is 0.85. So again, we can put these into StatCrunch. And then let's just look at, for just a minute, before we even find all those expected profits, it says if the CEO of the oil company is an optimist, believing the best things will always happen, then which site would they prefer? Well, of course, they're going to prefer B, because B, the optimists always look at where could they have the best case scenario. The best case scenario is that they make 120 million. So that would be B. Best case scenario. If the CEO of the oil company is a pessimist, they look at the worst case scenario, which means they want to look at where would they lose the most. And avoid that one. So in site B, they would lose the most. So they want to look at where are they going to lose the least. So the least amount that they would lose if they don't find oil would be site C. So that's probably where the pessimist would go. Okay, so let's take a minute and go to StatCrunch, and we're going to put all these in, and we're going to run them separately, and then we'll come back and make sure everybody has the actual expected values the same. So we're going to get a new data set here, and I'm going to put them all in. This is CP 6.1 page 164. Oil. Okay, so this is going to be profit A, prob A, profit B, profit C, prob C. Okay, so we have 80, negative 10, 0.2, 0.8. So we can just run this 3 times. Once you get your data in, and we're just going to save this. Make sure it saves. And we're going to go to stat and calculators down to custom. And we've got profit A, prob A, and we're going to hit compute. And so our expected profit for A, let's just write that in a different color. And that expected profit is $8 million. Okay, and we'll make sure we have these jotted down together. And then we're going to do it again. So calculators and down to custom. And this time we're going to choose profit B and probability B. And we're going to do the same thing. And our expected profit here is, ooh, it looks like we're expected to lose 4.2 million. Definitely don't want to choose that one. And calculators and custom. And the last one is going to be a profit C and prob C. And we're expected to earn 6.25 million, but still not quite as much as A. So let's just go and share our paper and make sure that we have the same thing, all of us. So we have losing 4.2 million and 6.25 million. So the CEO, if they were a statistician, they would go by looking at the overall expected profit of $8 million. So they would choose site A. Definitely site A. Okay, our last example is a probability example with gambling. And although we only recommend going to the casino with the amount of money that you are willing to lose, right? It should be something fun if you're going to go. Don't go there with the expectation that you're going to win enough money to pay your month's rent, because you will get into a cycle then of always betting to get caught up. We also have to know that a fair game is a game or situation in which the expected value of the profit for the player is 0. Not a loss and not a gain, but 0. That's considered a fair game. You may also hear that called a zero-sum game. So let's look at this situation. It says, a charity is holding a raffle and sells 1,000 raffle tickets for $2 each. One of the tickets will be selected to win a grand prize of 1,000. 2 other tickets will be selected to win consolation prizes of 50 each. And the rest basically donated their money. So let's construct a probability distribution for the player. So we have 3 outcomes. We could win the grand prize. We could win a consolation prize. Or we could just lose. So if we win the grand prize, it says the grand prize wins $1,000, but they did pay $2 for that ticket. So 1,000 minus 2 means their profit, 1,000 minus 2, their profit is $998. Okay, you always have to make sure that you take away whatever you bet as your original bet. The consolation, there's 2 of those, and they're going to win $50 minus their $2 bet would be $48, and everybody else just lost $2. So make sure you note that as a negative. Then the probability of each is just how many opportunities are there to win. So there's only one winner out of 1,000, and you can enter this into the calculator as such. There are 2 possibilities of winning out of 1,000, and we're going to assume that when we grab these tickets, they're all at once. So don't think of after this first winner is drawn, there's only 999 tickets. We're going to go with all of them out of 1,000. And then the other 997 people out of 1,000 all lost. So we're going to go to StatCrunch and put this in. It says, find the expected value for you as the player if you buy 1 raffle ticket. Describe what this means in practical terms. Okay. So we've got 998, 48, and a negative 2. And that's 997 out of 1,000 people. And that is 2 out of 1,000 people. And that's 1 out of 1,000 people. Okay. So here we are. So we're going to go to stat and calculators down to our custom. And our variables var1, our weights are in var. It looks like we have to turn this into the decimal. So that would be 1/1000. So that's going to be 0.001, 0.002, and 0.997. So 0.001. Okay, so we can use those. So stat calculators down to custom again. And then var1, and weights are in var2, and we can hit compute. And there's what we expect to, what? It's negative. That means we're going to lose money. So we are expected to lose $0.90 if they play part of this raffle. Okay. If a player decides to buy 25 tickets, what is their expected profit? If a player decides to buy 25 tickets, what is their expected profit? Well, each time that they buy a ticket, they're expected to lose 90 cents. So we're expecting that they're going to lose 25 times that 90 cents loss. So we're expecting to lose 90% of that. So 22.50 loss. And then it says, what is the house edge? So the house edge is opposite of the probability of winning. And so let's just go here. Share my screen so you can all see what I'm writing. So overall, we're expecting to lose $22.50 out of those 25 tickets. What is the house edge? It says the house edge up here is the expected value of the profit for the house, usually written as a percent. So the expected profit means they're losing money here, losing money here. They're winning when we're all losing, right? So it's the expected profit, the expected value of the profit. So they're expected to win. So if you turn this all around, they're expected to win at 99.7% of that time. And is this a fair game? No. And that's because, not because we're losing money, but because the expected profit for the player is not 0. And that's all. So we'll see you back for lesson 6.2 here in just a bit.